Hi, I am Lopa Mudrashen. Welcome back to my channel Electronic Science Tutorial. I will start a new lecture series on NTA UGC NET and West Bengal SET exam for Electronic Science subject. Those who are not follow my channel, please follow my channel. If you like my channel, then please like, share and subscribe my channel. So let's start our class. In today's class, we discuss about the NTA UGC NET and West Bengal SET exam 2022. In this session, we cover in detail about this topic so that we can easily solve the previous year question paper of UGC NET Electronic Science. Each and every topic we can understand in easy and simple manner. So, let's begin our NTA UGC NET exam 2022 class. Okay. Today we talk about the electric potential of PN junction diode. So this is the PN junction diode, its electric field and its electric potential representation or graphical representation of a PN junction diode. So how can we get the electric potential? If we integrate the electric field, we get the electric potential. In previous class, we can calculate or we discuss about the electric field of PN junction diode. In this topic, we discuss about the electric potential of PN junction diode. So now we know the electric field calculation. And we know the electric field in the P region and in the N region. So, from this equation, we can easily get the electric potential of PN junction diode. We can integrate the electric field and we get the electric potential. Okay. First of all, we can integrate the electric field in the P region. Then we get the electric potential. And how this is the calculation can be done in this way, that is electric potential phi x is the electric potential, that is equal to minus integration of Ex dx. Ex is the electric field. We know the value of the Ex, that is ENA divided by epsilon s dot x plus xp. This equation we get in the previous class, that into dx. So this is the equation 1. Okay. So from this equation, what we get? We get phi x equal to ENA divided by epsilon s dot x square by 2 plus xp dot x plus c1. C1 is the integration constant. The potential difference through the PN junction is very much important parameter rather than the absolute potential. So we can set the potential, that means electric potential is equal to 0 at x equal to minus xp. And so from this equation or from this condition, that is electric potential is 0 at x equal to minus xp, we can get the integration constant C1 value. So what is the integration constant value? That is C1 equal to ENA divided by 2 epsilon s dot xp square, because x equal to minus xp. Okay, and potential is the 0. So from this equation 2, we can get the integration constant value. and that is equal to ENA divided by 2 epsilon S dot XP square. Okay. So now if we putting the value of integration constant, that is C1, in the equation 1, we get the potential in the P region, and that is equal to phi x equal to E Na divided by epsilon s dot x plus xp square whole square. Okay, and this is the limitation. Minus xp greater less than equal to x less than equal to 0. So this is the potential in the P region. In same process, we can define the electric potential in the N region. And how can we define? That is phi x equal to integration Ex dx, and we know already the Ex value of N region, that is End divided by epsilon s dot xn minus x dx, and if we integrate this value, what we get? We get phi x equal to End phi divided by phi s dot xn dot x minus x square by 2 plus C2, where C2 is the another integration constant, and the potential is a continuous function. So that is equal to 0 in the junction region or in the metallurgical junction region. So at x equal to 0, we get the integration constant value. The potential is a continuous function, and so at the junction region x equal to 0. And if we put the value of 0, x equal to 0 in equation 4, what we get? We get the integration constant value C2, that is equal to ENA divided by 2 epsilon s dot xp square. Right? So this is the integration constant value of the equation 4. Thus, if we putting the value of integration constant in equation 3, what we get? We get the potential, electric potential value in the N region, and that is equal to phi x equal to End divided by epsilon s dot xn dot x minus x square by 2 plus ENA divided by 2 epsilon s dot xp square. This is the integration constant C2 value, and the limitation is 0 less than equal to x less than equal to xn. So this is the graphical representation of electric potential, and this is the electric potential value. This is the built-in potential. At x equal to xn, we get the built-in potential barrier. So the magnitude of the potential at x equal to xn, which is equal to the built-in potential barrier, that is we denote it, we referred it as VBI, or here we referred it as del V. So VBI, that is the built-in potential barrier, is phi x equal to xn. That means potential at x equal to xn, we get the built-in potential value. And what we get? We get E divided by 2 epsilon s dot nd xn square plus na xp square. Right? So this is the potential barrier value of PN junction diode at x equal to xn. So this is the built-in potential barrier. Okay. With this, we have come to the end of our session. I hope you like this video. Thank you friends. If you like my video then please do like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.